Okay, so oops, let me close this out. Um, Go ahead and load the data for today. Go and grab it from web courses and load it into SPSS and let me know when you are ready to go.
Rob, could you look for the slide?
Oh, yep. It's weird. They're listed backwards on the screen here.
Something better next time.
Oh, okay.
But your response is approved.
What is this? What is that?
I do that often. So
No, I know that. Those are great. It's appropriate though.
Yeah, the worst is when you're laughing. It has been said and you're like, oh, I'm so sorry.
Well, I checked and it doesn't say, but there's like a bunch of blocks.
That's better, right? You guys see that better? I mean, the important thing is that the output will look bigger, so we'll see how this goes. All right. Do we all have the data? Who doesn't have the data yet? While people are loading the data, let's talk a little bit about the homework. So I haven't looked at your guys' homework yet because it's technically due this morning. When you guys are doing the homework, you do not have to make your own APA style tables. I would encourage you to do it because it's good practice. You're going to have to do it for papers anyway. I see some of you smiling and laughing, which means you made your own APA tables. I appreciate that, right? I think it's a good practice to get into. In my next class, I do make people like there is no pasting the ugly ass tables that come out of SPSS into those papers. But if you don't want to, if you want to just paste a regression table in there, you can, or a correlation table, you can. Though again, I think there's value in making them yourself. For figures, you will make the figures yourself. And so the second portion of class today, we're going to go through, we're getting into the stuff that I really love to do when it comes to regression analyses, right? If you talk to, if at least you guys talk to the students that have had me before, I'm really picky about figures. I like figures to look nice. And I spend a lot of time trying to get them to look as cool as possible. And within the context of figures, I love regression figures that have like a straight line is a straight line, and who cares that But today I'm going to show you how to make some really cool figures, and I think building the figures yourself helps you understand the pieces of regression a little bit more. So we're going to go through it today. We're going to build curvilinear figures, and then you will also be building curvilinear figures for your homework. It's cool because we're starting to get into the stuff that I really love about regression, which is looking at these various functions of the slopes. Next week, we're going to talk about interactions in the context of regression, which I really love. And then we will start looking at interactions with curvilinear effects. And then we like from here on out, everything is just more fun in this class. And I know it's hard to say that statistics are fun, but I promise you, like everything from here on out is pretty cool. Today, we are going to take everything that we've been doing so far, and we're going to analyze a data set, and we're going to walk through the steps, and we're going to look at what could be going on as far as outliers, and then we are going to enter things into blocks in order to look at curvilinear effects, and then we are going to graph those curvilinear effects. And that will be the same kind of thing that you do for your homework this week. Does everyone have the data loaded? Rebecca? We're waiting on Rebecca. While we're waiting, anybody have are any of you podcast junkies? David?
I wouldn't say junkie, but yeah.
What's your favorite podcast?
There's this one called the Partially Examined Life. It's a philosophy.
Okay.
Serial killer stories.
What'd you say?
Serial killer stories.
I didn't hear you.
Murder. Serial killers.
Oh, serial killer stories. So do you have a favorite one? Like-
Not really.
No? Okay. I like some of the real crime ones. Yeah. David, what do you like?
Stuff you should know and entrepreneur.
I used to listen to Stuff You Should Know. Entrepreneur's not bad. I haven't listened to that. I've only listened to a few episodes of it. If you like stuff like that, How I Built This is also a good one where they interview like CEOs of major companies and kind of how they got. It's amazing how small all of these people start and what they build, right? The Patagonia one is one of my favorites. So anyway, that's cool. A bunch of business people, and none of you listen to Planet Money? Yeah. Oh, we got a Planet Money fan over there? I love Planet Money. So they had a new episode that came out last night or yesterday. They're doing a series on antitrust right now. I know this sounds boring. Oh my God. Like they make antitrust so interesting. I love it. If you don't listen to Planet Money, you're missing out. It's one of the best podcasts out there. So, Rebecca, are we good to go now?
Okay.
Everybody else good? We all got data? Who said that? Sam?
I can catch up.
Yeah, our computers are restarting, so it's
Yeah.
going to be a while.
Oh my goodness.
They do that every.
Okay, so that's okay. Watch. Well, God, you know what? I hate to do. Watch what I'm doing. We can go back and walk through it. The nice thing is there will be video for you regardless because we're recording. All right. So what we're going to do today is we are going to look at curvilinear relationships. In the video for this week, I briefly hit on 4 types of nonlinear regression models. We talked about curvilinear regression models, data transformations, and that's going to be the 2 things that we talk about today that we really focus on today. Then we have logistic models when you're predicting the likelihood of an event. Then we have these Poisson models, which tend to be, it's not just Poisson, so there's a whole kind of family of generalized linear models. You know, within the context of regression, we have generalized linear models, and those are things that allow you to do all kinds of funky stuff with your dependent variable without actually transforming that variable. Then we have the general linear model, which assumes some sort of linear relationship, and you can't change that dependent variable unless you manually do it yourself. And within the context of the general linear model, we're assuming that everything is roughly linear. But the generalized linear model doesn't necessarily make that assumption, and so it allows you to specify outcomes for your dependent variable that have a gamma distribution, for example, and that's a continuous, heavily positively skewed distribution. What we oftentimes see in like blood alcohol content, we see a gamma distribution for blood alcohol content, where the vast majority of people have blood alcohol contents that fall between like that 0.0, people who are drinking, that fall between that 0.01 and 0.1, and then they start to taper out to all the way up to 0.2, and if you're really in rough shape, 0.3. It winds up making, I'll do it backwards, this distribution that looks like this. But it's also like roughly continuous because you can have 0.1, 0.111, 0.1123, you know, you can have all of these various numbers in there. Whereas if we're talking about just number of drinks, it could be 1, 2, 3, 4, up to however many drinks that a person reports consuming, but it's not really continuous because we don't ask them if they drank 1.17 drinks, right? It's a count, it's a frequency of drinks that they had. And so we fit those frequency of drinks using something like a Poisson distribution, or more commonly now a negative binomial distribution, which allows the variability to kind of slide around in there. But what we're going to be focusing on today is not logistic models or count models, but instead curvilinear models and data transformations. How are we doing with computers? We're slowly getting there. So the question that we have, we're going to pose a research question. We're going to look at our data. We're going to look through the graphics of our data. We're going to identify outliers and problems. Then we are going to run our regression models, and we are going to enter them in steps like we've done with the homework for this week. And we are going to arrive at a final regression model with both quadratic and cubic functions, or at least we're going to test for those across steps. Once we're done, we are going to figure out how to graph each one of those, or each one of those slopes, and then come up with a final graph for the slope of our predictor variable. In this case, we're going to look at protective behavioral strategies, which is a variable that we brought up in class several times. And we're going to look at alcohol consumption as our outcome variable. So protective behavioral strategies are behaviors that people can engage in when they're drinking to reduce the amount that they drink or reduce the amount of problems that they have, right? So let's do something real quick. Let's just have a look at our two variables. So we have, let's go graphs, analyze, descriptives, explore. Let's remove that. And let's put in PBS. Oh, before we do this, switch over to variable view. Find PBS, it should be at number 5. And in label, just type PBS. Then come down here to number 12, where it is drinks. And in label, just type drinks. And then we can go analyze, descriptives, explore. And let's put PBS over here. And let's put drinks over here. As far as statistics, we can grab outliers. That doesn't hurt. Plots, normality plots, stem and leaf, histogram. That sounds good. We don't need to worry about options. Are we ready to go? Everybody here? Go ahead and hit OK. And you know what? Let me try and do something here as well. I don't care about that. Outline size, small. But what I do care about is font. And let's try and make this font. Oh, it won't actually let me make it larger. Never mind. Can everybody see this okay? See our output okay? All right. So what are the things that we're looking at here for PBS and for drinks? We want to look at skew. So we have a little bit of positive skew for PBS. Doesn't look bad though, right? And we have a little bit of positive skew for drinks, but also doesn't look too bad. We have a range for PBS that goes from 1 to 6. This is the first thing that we want to check. As we're checking our descriptive statistics, 6 should not be a value. So this means that we have too many people that are getting counted here, because our range for PBS should only go from 1 to 5. 6 is when people select do not wish to respond. So we're going to have to go back and fix that, because ranging from 1 to 6 is a problem. The other thing, let's scroll down. The rest of this doesn't look too bad. If we look at drinks, our mean is 1.295, standard deviation 0.03. Our range for drinks, 0 to 3.67. 0 is also a problem, because if we want to know what the effect of protective strategies are on the amount a person drinks, then we can't have non-drinkers in there, right? It just doesn't make any sense. Some of these things that we're doing with data cleaning wind up being methodological and or theoretical things that you have to know about your study, right? So if I know that I want to look at alcohol consumption, I want to look at alcohol consumption amongst people that drink, not amongst everybody, right? It doesn't make any sense to look at it amongst everybody. So we're going to have to go back. Yeah, go ahead.
I don't know if this is a weird question, but my descriptives table, me and Daniel's descriptive table, it doesn't look like yours. It has like PDS like 0, 0.33, 0.67, 1, like that.
Say that. Are the numbers different, or is the entire table?
So your the number for the minimum and maximum is like correct here, but then it continues on like 0.3 and like
Yeah, we have it so
7 and 1 like the
also don't have it compartmentalized like drinks and bottles.
Yeah. I mean, I guess it's fine if you get the like 0 0 thing. I think that would be the same information, but it's just like I didn't know what to do with questions.
Does everybody else do that also? No? All right, so you guys up front here.
Okay.
Again, I can't emphasize how much I hate SPSS. I can't emphasize that enough. Okay, so anyway, yeah, just look at the first one, guys. All right. Here are our extreme values, potential outliers. As we scroll down, we do see that there's something kind of weird going on with PBS. Obviously, from like here on over, that shouldn't even be there. This is not necessarily weird, but my guess is you have a bunch of people not endorsing PBS because they don't actually drink, right? If we continue, but the distribution, aside from these weird things, looks fairly decent, right? It looks like a rebel ship, which it should, a rebel starfighter.
Oh yeah.
Our QQ plot doesn't look too bad for PBS. We can see that we've got outliers on both ends, right? Drinks, it looks weird because we've got all of these zeros. If we didn't have all of those zeros, drinks would look very nice, right? We know that that's going to cause a weird thing in our QQ plot, and it kind of does up here. And so we have this is a heavily skewed box plot, right? So let's do this. Before we go and remove those variables, let's go analyze, or those observations, regression, linear. We've got PBS in there already. Let's add drinks as our dependent variable. Statistics, can check all of those things. Estimates are fine. Plots, we want to plot our predicted over our residual. So Z-pred over Z-resid. And what should that look like? Do you guys remember? It should just look like a cloud with a mean around 0, right? And a nice kind of circular cloud. Save, let's save our standardized and unstandardized residuals and predicted values. Options, that's fine. All right, go ahead and hit run. Let's check this out. And we can see that PBS is inversely associated with alcohol consumption, which is what we would expect, right? It accounts for, where's our R squared at here? Right here, 0.027% of the variance in alcohol use is accounted for by PBS. There's our frequency of drinks. This is our normal PP plot. That doesn't look too bad, right? It's sticking pretty close to this line, which means that I'm guessing when we get to our looking at our predicted residuals by our or our residuals by our predicted values, that we're going to have a pretty decent circle. That would be my guess. And it's not bad. There's something weird going on over here, right? But here is 0 and 0. And so we kind of have this nice circle. There's a few weird oddballs and something strange going on there. But if this was cut off right here, then that wouldn't look too bad at all, right? Let's go back and let's go data, select cases, go select cases if drinks is greater than 0 and PBS is less than or equal to 5. PBS is less than or equal to 5. We all there? Hit continue and OK. If we flip over here and look at data view, we should have some little crosses, and we do. All right, let's run our exact same regression model that we just ran. Let's have a look at this. So we lost some observations, right? 491 is where we're sitting now. Before we were at 670. So we've dropped down. We expect the relationship between PBS and alcohol use to be much stronger now because we've removed people who didn't want to answer PBS, and we have removed people who say that they don't drink. And that is exactly what we see, a very strong relationship, minus 0.590. And our distribution of PBS, or of drinks looks pretty good there. That looks really good, right? That is a very tight kind of PP plot right along that line. Our circle looks pretty good. Our cloud of data, right? We've still got some oddballs out here that might be exerting some influence, but we're not going to worry about those right now. This looks pretty decent. Let's do one other thing. Let's go graphs, legacy dialogues, and scatter/dot. We'll select a simple scatter plot, and we're going to scatter drinks on the y-axis by PBS on the x-axis. And this is going to help us try to determine if we think that there's a linear relationship or a curvilinear relationship, or if something kind of different is going on here. Hit OK. And this is the graph that we get. What kind of a relationship does that look like? Looks kind of like a negative relationship, right? Like if you were to start like right here, but there's also the fact that it seems to have like a positive relationship followed by a negative relationship, right? It looks like we've got some sort of a curve going on here, possibly, or just a straight zero relationship. One of the best ways to determine if you have a curvilinear relationship, at least to start testing for one, is just to look at your data, right? Plot your data against each other, look at some scatter graphs, and see if it makes sense to go that direction. In the video for this week, I had said one of the assumptions that we typically make in social sciences is that the relationship between two variables is almost never linear, right? There's almost always some sort of curve. And so if you make that a priori hypothesis that there's a curvilinear association, then it's fine to test for it. You can also just say that you tested for a curvilinear association, at which point you're not stating an a priori hypothesis, but you're saying we explored, right? We explored a potential curvilinear relationship. And for the most part, reviewers are okay with that because that's the way that nature often flows, but not always. So anyway, we've gotten to the point now where we think that we might have a curvilinear relationship. What do we need to do to analyze this data and arrive at that conclusion? There's some steps that we have to walk ourselves through. What is the first step that we should walk ourselves through for any regression model that we're ever going to run from this point forward until the end of time? Nobody? I talked about it a little bit in last week's video and in the week before's video and in this week's video, and it is something that we need to do with our data. It's a linear transformation of our data.
Is it the centering?
Centering. We should always go and center our data, right? Like this is one of the most important aspects of regression. Let's talk about this for just a second. A regression model is y equals a plus b, b1 x1 plus b2 x2 plus e. And so in this, what is a? What is that? That is your basic intercept, right? And your intercept is what? It's your average of y, controlling for all of these other things, right? And what is b in this case? The slope of x, or of x1 here, right? And this, we did something last week, if you remember, that meant that our intercept would actually be the exact mean of y. What was it that we did that made our intercept always equal the exact mean of y? We centered these things, right? You center x1 and you center x2, then this becomes the exact intercept of y. Why is that? What's going on when we center it? If you ran a regression model with no predictors, then you would get what's called an intercept-only model, right? And that is just the, yeah, exactly, right? And it is equal to the mean of y, right? It's a flat line that runs through it. This marker is dying on me. If we want to get that intercept-only model, then we have to find a way to cancel out this and this.
Is it by subtracting the population?
It's not by subtracting the oh, it is. I mean, well, so it's by subtracting the mean of each one. Because what we do when we center, right, is we actually make this 0. Because this little relationship here is whatever slope b is times the mean of x in your data, right? And this is the same. It is the relationship, this multiplication of b2 times the mean of x, right? And that's how you work out a regression equation. It's just the mean of y plus the slope times the mean of x plus this slope times the mean of x2 plus error, right? Because we're not talking y hat, we're talking y. And so if we center it, then it is this slope times the mean, which is 0, plus this slope times the mean, which is 0. And it cancels all of that out, and we're just left with this. If you run a regression model that's not centered, this slope won't change, this slope won't change, error won't change, this will change, because it's controlling for where that mean of y is as a function of everything else in the model. So when we say controlling for, that's really what we're saying. We're controlling for the mean effect of x, right? And the mean effect of x2. And so if we set the mean effect of x1 to 0 and the mean effect of x2 to 0, then controlling for them means that y, or I mean a, our intercept, will be equal to our average level of y, right? So that said, we're going to come back to this because it's going to be very important when we go to graph things. But we should center everything in our model to start with. You can, by doing that, it's going to help you later on when it comes to graphing things. But it also allows your intercept to have real true meaning, right? That intercept now means the exact center of your data of y, the exact mean of y. It doesn't change these. These will never change, right? Your slopes won't change from centering. All it does is it allows for us to glean meaning from the intercept. So let's do that. Let's center our variable, which is, I didn't go through this, but centering does something else really important. I talked about it in the video. Does anybody remember what it does? So it does this intercept thing, which is great, yeah. But it does something else which is even more important. It allows for the reduction of non-essential multicollinearity, right? We have essential multicollinearity, which is just going to be the relationship of variables because you're multiplying two variables together. But there's non-essential multicollinearity, which happens when you have data clumped at various spots, and then it's multiplied by itself, and rather than being centered across. So we can actually look in a regression model and see the difference between non-essential and essential multicollinearity, and it can have a pretty drastic effect on the predictive ability of a model. But all right, so if we go analyze descriptives, explore, we have PBS in here, we have drinks in here. Let's just get our mean for PBS and our mean for drinks. PBS, the mean is 3.2937. So let's go transform, compute, C underscore PBS equals PBS minus, where'd you go, you? 3.2937. We hit OK. We have a new PBS variable. Dang it. Where'd my... And drinks is 1.7363. So let's go transform, data. No, that was right. Transform compute. Oh, wait. I don't know why I was doing that. Do we need to center drinks?
Is it just the predictor that you center?
Yeah, drinks is the outcome variable. We do not center drinks. You should never center your outcome variable, actually. So we've centered PBS. And we can run a regression model. And if we do something here real quick, let's just do this. I'm going to go regression, linear, and we have PBS in there. I'm going to pluck that out, and I'm going to put the centered PBS in. And how is this going to be different from the last model that the last regression model that we ran with the uncentered PBS? Will the R squared change? Nope. Will the slope of PBS change? Nope. What will change? Constant. Yep, intercept, right? So if we look at this, let's just double check that that's the case. Our intercept here is 1.736, and our slope is minus 0.590. Let's scroll up to where we ran this regression model before. Our intercept here was 3.678. And our constant minus 0.590. That's a big difference, right? We can quickly see if we come back down here, descriptives for drinks, 1.7363. And if we come down to our regression model, that should be equal to our intercept, right? Or at least very close. It's not perfectly centered, but 1.736. Those are roughly the same numbers, right? 1.736 and 1.7363. So when we have our variable centered, our slope doesn't change, but it gives our intercept meaning, and here that meaning is the true mean of that variable. All right, so we have centered PBS. All of these things are roughly the same. What is the next step if we want to examine a curvilinear relationship? We square it. Yep, we square it. Now, we're multiplying PBS times PBS. That's what squaring it is, right? Next week when we do interactions, we're going to be multiplying x1 times x2, but it's the same thing. It's a multiplicative term. Let's do this. Let's go transform, compute. Let's go C PBS 2. And you can go C PBS, and you can either do that, or you can use the little tilde and put 2. So we're going to square this. And let's do something else. Let's go transform, compute, and let's make regular PBS squared as well. All right, so we've created two new variables, centered PBS squared and PBS squared. Let's go analyze regression, linear. Let's remove CPBS for the time being. Let's just put in PBS. And in our next block, let's put in PBS squared. We're going to hit go. We're not even going to look at this. We're going to come back. Well, actually, we can look at it real quick. If we scroll down, you can see that in this first block, we can tell from this right here that PBS accounts for about 17% of the variance in drinks. And when we add a curvilinear relationship, we get roughly another 4% of the variance accounted for. And that is a statistically significant change. It's a 1 degree of freedom change and an F change in your model of 21.703. You can, SPSS gives you this. It tells you it's statistically significant. But if you didn't know this, how would you find out if that change was statistically significant? If all you had was a change in F, what could you do?
But we don't have the significance.
Right. Let's say that you don't have the significance. You have a change in F, and you know that you have a change in degree of freedom of 1. What could you do? Perfect. An F table, right? You could go to an F table. You could find your significance level. I mean, assuming that you're using an alpha of 0.05, you can go across to 0.05. You can go to your 1 degree of freedom, and then you can shoot across, and you can find what your cutoff is for a 1 degree of freedom at 0.05, based on the sample size that you've got, right? And it should be roughly 3.84. So 21 is a huge change in F, right? We know that this model fits better. Let's look at our regression model here real quick. Here's PBS1, PBS2. We see that actually it's kind of weird, right? Like in step 1, we see a negative relationship between PBS. In step 2, we see a positive relationship followed by a negative relationship. That means that it goes up and bends down. And that's kind of what our data looked like, right? It went up and it bent down. However, and actually if we look at these things, that looks pretty decent. Our residuals look decent. That distribution actually looked really nice. There is a problem in that we have a ton of multicollinearity accounted in that model. What's that?
VIF is 47.4.
Yeah, right. So let's go back to that. Our VIF, does it exceed our value of what we want? What is the value of VIF that we actually want to see? Less than 10 ideally, right? So let's go back to our regression model. And let's go linear. We're going to leave drinks in. We're going to pluck this out. We're going to go back here and we're going to pluck this out. And let's put in PBS centered. And then go next. And let's find PBS centered here. And all of our other stuff stays the same, and let's hit run. Does our R squared change, or should our R squared change? Should not change, right? And it doesn't. Our R squared looks the same as it did before. We have 0.073. We have a change in F of 21 with 1 degree of freedom. That model looks good. Everything looks pretty decent there. How about this? It looks a lot better, right? And we can see that our predictors are now doing kind of what we assume that they should be doing. We removed that, when we remove that non-essential multicollinearity, actually what we get is a negative and a negative. Now, when we looked at our data, we thought that it looked like positive and negative, But when we run this, it looks like it is negative and then more negative. And actually what more negative means is it switches directions, right? So if it's positive, then it's going to make whatever direction it's moving in stronger. If it's negative, it'll make the other direction stronger. And so we have two negative effects here, and they're both statistically significant. And notice our VIF. Huge difference, right? VIF looks reasonable, which means we've removed that non-essential multicollinearity. That graph looks good, that graph looks good. That data should look exactly the same as it did before, and it looks exactly the same as it did before. All right, so we have now done, we have centered our data, right? We have, actually, if we take a step back, we first examined our data. We identified that there were some observations that we needed to pluck out. One, because they were not true values, PBS being greater than 5, and the other, because we had non-drinkers included in there. We removed those people, and we looked at our cloud of data, and our cloud of data didn't look too bad. And in fact, after removing those people, prior to removing those people, we had all kinds of outliers identified in our box plots. When we plucked out that bad data, we're going to call it bad data. It's non-theoretically relevant data. Our outliers disappeared in our box plots, right? And then we went ahead with our first regression analysis. In our first regression analysis, in order to do it, we did the one thing that we should do before we run any regression analysis, any final regression analysis, right? And that is what? Centered our data. We centered our data, and then we formed a quadratic interaction or a quadratic effect, right? And then we compared non-centered to centered, and what do we find with regard to R squared of our model between centered and non-centered? No change, right? It's the same model, has the same predictive value, but we know that there are some issues with our slopes and our coefficients because of what? In the uncentered. We have a highly inflated VIF, right? Because we have not removed that non-essential multicollinearity. We remove that non-essential multicollinearity, our R squared doesn't change, our predictive value doesn't change, but our slopes change pretty drastically, right? We know that we're getting at least accurate slopes at this point because our VIF and our leverage statistics suggest that they're well within normal ranges. So we can move ahead with our analysis. We have one more thing that we need to do now that we need to test for, and what is that one last thing? The cubic effect, right? There is the question of, does it have a cubic effect? So how do we do that? What is our first step? Our next step, I'm sorry. How are we going to test for a cubic effect? Yep, so we go transform, compute. We have, I'm going to change this to C underscore PBS. Did I use a capital C before? I think I did. PBS 3, and this is going to be CPBS times CPBS times CPBS, or you can put CPBS tilde 3, right? We create this here, and our variable has been created. Analyze, regression, linear. Let's look back. Here's block 1. We have our centered PBS. Block 2, we have our quadratic effect. And in block 3, we can add now our cubic effect. Are we all there? We all caught up? We all tracking?
What were the first two? The blocks?
The first block is just PBS,
Okay.
right? And then we want to know what happens when we add the quadratic effect, and then what happens when we add the cubic effect. We hit go.
So you just follow it.
Yep, right, we're just adding steps here. Here's our model summary. Most of this stuff should look fairly consistent to how it looked before. We see that our R square is changing from 0.17 to 0.205 to 0.245. F changes dramatically across models, 1 degree of freedom change results in a significant increase in F, and obviously our p-values are far less than 0.05. If we scroll down now to our regression models, here's our simple regression model minus 0.590. When we add this in, this slope drops just a little bit, and then we have this new slope. And when we add in our cubic effect, we see that these things change slightly. This actually gets a little bit stronger. This gets a little bit weaker. And now we have a positive slope here, right? If we look over here at our tolerance or our collinearity statistics, tolerance, what do we want it to be at? Above 0.1. It's above 0.1. Those look pretty decent. VIF, below 10. That looks pretty good. And then if we scroll down here, that doesn't change. That looks good. Our data cloud looks really good now, better than it did before. We've still got some weird person out here. We could, if we wanted, try and identify this person, or you don't have to try to identify this person, actually. It's easy to identify this person. How would we pluck this person out of our data? Let's say that we've decided that this person is not good for our data. How do we find that person?
Frequencies?
It's going to be tough for, actually it wouldn't be tough for frequencies, but what would we look for in frequencies?
So we will look, like it will be only once, but the value of this person will be very high than the other values. It's like 10, then we'll start from 2, 3, and this will be like exactly 10 or something like that.
Sure, you could do it that way, absolutely. What's an easier way to do it? Just looking at this chart, you can figure out who that person is, right?
Did you look at the range?
Yeah, like this is the only one that has a standardized predicted value less than -4, right? So we could easily just go and select cases and remove the person if their standardized predicted value is less than or equal to -4, right? I can tell you right now that one person is not going to matter one bit for our analysis, so I'm not going to drop them. What I would do in an analysis in a paper, I would say that we identified a multivariate outlier, right? Because you do have a multivariate outlier here. You've got this one person whose residual is way outside of the norm. And I would say we ran the model both with and without that person. And despite being an outlier, they weren't exerting significant effects. I am the type of person that is biased towards keeping data in. Other people are biased towards removing any type of abnormal data. I think psychologists tend to err on the side of keep data in because we know that data is messy and people are abnormal, right? And so it helps us get like a closer approximation to reality in those models that we run. Sometimes that means that those models are messier, but that's because people in life are messy, right? So we have looked at our data. We have removed nonsensical data. We've identified an outlier that we're not going to remove, but we've identified them at least. I feel pretty comfortable about this distribution of residuals. It's not a perfect circle. It's kind of a rectangle, but it's not bad. Our PP plot here looks good. Everything looks pretty dang good. What is our next step? Actually, before we do that, how would you write this up? What would you say? Let's start with the planned analysis section. If you say you have data preparation and planned analysis, what would you say there? There's some points that you want to hit in this section, right? What are the important things to hit in a data analysis and data preparation section?
The steps and how you choose.
Yeah, so the first thing I think, the first thing to say is, we did traditional data cleaning. We examined univariate and multivariate outliers, right? Actually, the first thing is we removed non-drinkers and people who did not endorse PBS use, right? And then you would say this resulted in a change from 670 to 491. All right, we dropped. We lost about, 80 people. We lost 80 people when we did this. Nope. we lost 180 people when we did this. So 180 people that reported that they didn't drink or that they didn't use or refused to report PBS. That answer for 6 on PBS means do not wish to respond. And so we just plucked them out. In truth, we should probably use missing data to handle those people. But we'll talk about that later. We're not going to talk about it right now. Yeah, go ahead.
Why even include that option?
What do you mean?
Like the 6.
Why include do not wish to respond?
Questionnaire.
Because IRB makes you.
Oh,
You can't force responses, right? People have to have the ability to say, I don't want to answer this. And so if you force them to respond to something, then you have to have an option that says, I don't want to respond to that thing. And as long as you've got that, then you can force a response. But the response can be, go screw yourself. So anyway, yes, we removed these people. Then we looked at, then what was the next step after removing those people? Centered our data, right? We centered our data, and then we looked at univariate and multivariate outliers, right? Distribution of residuals appeared fairly normal. However, we identified one potential multivariate outlier. You can even say at this point, data was analyzed with and without that person, and they didn't exert significant influence, or they did exert significant influence, right? You do not talk about tolerance or VIF in this portion. This is something that you're doing on your own to make sure that your model is good, that your model is appropriate. You don't have to put it in there. That's not necessary. It can be necessary if you're talking about, hey, I have these 2 different variables that I thought were different, and I added them into the model, and my VIF was 47, which lends me to believe that these two variables are so close to being the same thing that they're screwing up the model. Church it up a little bit. Don't say that, obviously, right? Don't say screwing up the model. But yeah, you can use VIF in that type of instance, but you don't need to use it when you're forming interactions or forming quadratic effects or so on and so forth. The next thing that you did is you formed both quadratic and polynomial effects and tested those in the context of the regression model. That's all you have to say. You don't have to say anything else because we're talking about like, here is the analysis and here's how I got ready to do that analysis, right? The results are where you talk about what happened in the analysis. So if we move now down to the results section, the first paragraph of your results section should always be what? Descriptive and bivariate statistics, right? Where you talk about kind of means and ranges and basic bivariate relationships between variables. You can also talk about whether or not these things varied as a function of gender or biological sex, right? If there were differences. How do you find out if there's differences between males and females on drinking or PBS? Simple t-test, right? Yeah, of course. Same thing applies with age. All right. So, and if you want, you can also compare the people that you removed from there, right? Like, hey, there were X number of drinkers and they didn't differ by age, or perhaps they did because non-drinkers tend to be younger, right? That's what happens in college populations. Anyway, we talk about descriptive statistics, and then we move into our regression analysis. And we start our regression analysis by saying alcohol consumption was regressed in step, you can start with in step 1, alcohol consumption was regressed onto mean-centered PBS, right? This accounted for roughly 17.5% of the variance in drinks. And then provide your F statistic. F, blah, 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 for your model, right? F, degrees of freedom, and whatever F was. That's it. That's all you say for step 1. Do not talk about your slopes in step 1, because if you notice between step 1 and step 3, our slopes change a little bit, right? So you can say there is a significant negative relationship between PBS and drinks, but it makes no sense to list the slope now and then list it again in step 2 and then list it again in step 3. Just say that it was significant or it wasn't significant. That's fine. In step 2, the quadratic effect was added to the model. This resulted in a significant improvement in overall model fit evidenced by a change in R squared of 0.04 or whatever that change was, 0.035 or something like that, right? And then put change in F with 1 degree of freedom, and it was like an F change of 24 or something like that, right? If you look at your total F for that regression model, it is right here, 53.915, right? So you can report, here's your change in F was right here, and you can see that F is just coming down with each one of these, right? And your change in R squared, you can list your change in R squared. And that's really the most important thing is, are we explaining more variance in this? And we did. We explained, an additional 4% of the variance. And then we could say the negative association between PBS and drinks consumed was still statistically significant in the step 2 model. And the quadratic effect was also statistically significant, right? And negative if you want to throw a direction in there, that's fine. What's next? Step 3, we added the cubic effect to the model. This resulted in a significant improvement in model fit and an increase in variance explained by PBS of roughly 4%. What does it say there? 4.041, so 4.1%. And then you can put your change in F and change in degrees of freedom and so on and so forth. And you don't have to put, I'll just say you don't have to actually put change in F and change in degrees of freedom. You can just put change in R squared, comma, P is less than 0.001. It's totally okay. I know that, I seldom actually put change in F or change in chi-squared depending on the type of test that you're doing. I will often just put the change in R squared because that's all that anybody really cares about. But and they're equivalent, right? If you have a significant change in F, you're going to have a significant change in the R squared. Sometimes that R squared is nothing, like 0.01, and yet you still have a significant change. So, all right. Then we get to the most important point of this analysis, right? You say the final model. In the final model, we had a significant negative association between PBS, a significant quadratic effect of PBS that was also negative, and a significant positive cubic effect of PBS. These effects are listed in table 2, right? And that's where I would put that. You can put those in table 2. You can actually put your changes in F, your change in R squared, degrees of freedom, all of that stuff into a single table, which would be like roughly consistent with combining this table, roughly consistent to combining that table to this table, something along those lines, right? And then the last step, which is what? The curvilinear relationship between PBS and drinks is depicted in figure 1. And so now we have to make figure 1. But before we make figure 1, we're going to take a break because it has been 1 hour. Do we have any questions before we go on break? Shoot.
So, like if we don't center the variable, but still our BIF and tolerance are okay, will the regression become invalid? Will it be questioned by the reviewers? Or
No. In fact, no, I don't. Like people aren't going to do that. And you actually see you see this all the time in growth modeling, right? Because oftentimes in growth modeling, people don't want to center the variables. They want to know what the growth actually looks like from 0 up until X number of time, and whether or not there's quadratic changes in growth. And so, no, people oftentimes, the reviewers won't question it. It does become more tricky to graph those things. And the coefficients, can be very, very different. But keep in mind, those coefficients take on different meaning if a variable is centered versus not centered, right? So.
And what if, like, after centering, we lose the p-value? Like, sometimes just after centering, the model is becoming insignificant, but if you don't center it, it's still working.
Yeah, so this is a good question, and this does obviously this happens, right? Um, if you lose that p-value, um, and prior to centering the VIF was fine, it may not be it may not be a huge issue if the VIF was fine in the first place, and this is why it works in linear growth modeling because you don't have bulges in your data because every time point is equally spaced across, right? And so if your VIF is fine, it probably means that your spacing within that independent variable is fine and centering is not required. Um, Though I feel like, and I can't tell you this for sure, but I feel like if that's the case, you probably won't lose that p-value. It probably won't go non-significant. If it does, you'll have to dig into it and try and figure out like what's going on. Why is this happening? But yeah, there's never just a perfectly right answer, right? I can tell you what the wrong answer is, and that is I'm going to keep this analysis because I have a significant p-value, and like that's the wrong answer, right? But yeah. Any other questions? All right, let's go on break.